Today is the last regular lecture for this course. Then we have this lecture, and then we have final exam. So we will take the final exam on Thursday, so June 15th, and then during the regular class time. So actually, I think the difficulty level of the final exam maybe maybe is similar to the difficulty level of the midterm. Okay, so then we will take the final exam on in the group number 32, 302, and 303, right? Not 304. And then it's a closed book exam, and then exam will cover chapter 3 and 5. So chapter 3 is the sequential logic part, and then chapter 5 is the basic digital building block, and then also the final exam will cover the system value part in chapter 4. Okay, then also and no electric devices are allowed. Okay. Are allowed. No. Okay. Right. Okay. So in today's class, we will learn about memory block. So then actually, the system, the data, our data is stored in memory components. Okay, so actually the memory is very critical. It means that very important component in modern system, because the modern system handle a large amount of data. Okay, then in order to improve the performance, of our system, then we need to use the memory component very efficiently. Okay, so the memory is very important part of our computer system, also in our digital systems. Okay, let's learn about the memory array. Then, so we know that our data is stored in memory. Okay, and it means that we need to access. So access means that we need to read and write our data through the memory. So it means okay, and then we access memory component like the array. So what is the array? So array, we can declare array like this. Okay, so n is the index of the array, and then each array has the elements. Okay, and then data is stored in each element of array. Okay, so and then we can understand the memory components like this. So this is the memory block that you can find the address here, and then data is here. So and then actually in the memory, the data is stored like the data array, the data, and the data is indexed by address. Okay, so in this example, the bit width of the address is n bit, and then the bit width of the data is n bit. So which means that the size of a single element in this array is n bit. Okay, n bit. So it means that we just access this memory components with the width of is n bit. Okay, so we can access like the data 0 or data 1. So if we want access a certain data inside of the memory, then we can access this data like data index number 0 and the data index number 1. Then the size of this data is equivalent to the width of data port. This is MB. And then I mentioned that you can access a certain data inside of a memory with address. So address is MB. Okay, this is the binary number. So with the MB, then we can represent the index number from 0 to power of n minus 1. Okay, so with the NB address, then we can access the data inside of the memory component, and then the range. The range of address is from 0 to the power of n minus 1. Okay, so that is the basic definition or basic composition of the memory component. Okay, so in order to read the data for this array, then we can actually in the behavioral model. So not a real model. So this is behavioral model. So we can read the data like data and then address. Okay. The address indexed by address. So we can write the data to the memory like the data address equal new data. So a certain data like A. So we can understand the memory like this. So memory is the array of data. Then we can store this data in this memory array, and then we can access data in the memory component using this address. Okay, this is the basic composition. And then this is what I explained already. So I mentioned that the width is the size of a single data element. And then what is depth? So actually when the data is stored in the memory, then the data element is indexed by address. Okay, so address represents the data index. And then so in this memory composition, then it's width. So this is called the width. That is the size of a single data element. And then the number of data elements. The number of data elements is called depth. So depth of array. And then, as I mentioned, this is the address. So we can. So in this example, we can calculate the size of the memory, right? It's obvious, right? So what is the size of the memory? The size of the single element multiplied by depth. So we frequently represent the size of the memory like the width multiplied by depth. Okay, obviously, right? Okay, so in this example, the width of data is 3, right? And then so depth, what is the depth? Depth of this array is 4. So which means that we can access this memory with the 2 bit of address, right? If we have 2 bit of address, then we can access 4 different elements inside of the memory. Okay, so the size of this memory is 3 bit multiplied by 4 is a 12 bit. Okay, obviously. So okay, this is the example. Then also another example. This is the large memory. So and then sometimes so actually we call a single element of a memory as word. Okay, so word is a single data element in the memory. Okay, that is the word. So in this example, this memory is the 1024 words multiplied by 32 bit. So what does that mean? So it means that this memory includes 1024 words. So which means 1024 data elements. So that is 1024. So this is the 1024. What is the data bit? So 32 bit. So that is the size of data, size of a data element. So data bit is 32 bit. Okay. So size, what is the size of this memory? So 32 bit is the 4 byte, right? It's a 4 byte because the 1 byte is the 8 bit, and then 1024 words. So which means that there are 1024 data elements. So what is the size of this memory? 4 multiplied by 1024 is 4 kilobyte, right? Because 1024 is kilo in this system. Okay. So we can calculate the size of the memory like this. Then what is the width of address bit? In order to represent 1024 different indexes, then we require 10 bit. Okay, because 2 to 10 is the 1024. Okay, we can calculate the specification, that is the composition of data, composition of memory like this. Okay, and then let's see how data is stored and data is accessed inside of memory. So this is the basic. So this is the basic structure of memory element. So our big data. So actually, I mentioned that we use memory to store our data, and then our data system has binary data. So which means that binary data is composed of many bits. So in order to store one bit, so this is the stored bit. So the bit data is stored inside of this rectangular part, the stored bit, and then this part is called the bit cell itself. Okay, so our bit data is stored in the bit cell inside of a memory. And then how can we access the bit cell? So in order to access the bit cell, then we need to control the access to the bit cell using the word line. So what does that mean? So this word line is connected to the one port of the bit cell. And then this word line is used for activating. So activating means that if we activate this cell, then we can access. So we can read and write a data bit stored in this bit cell. So we use word line to activate or deactivate a single bit cell. And then, so this is you can think that this word line is the control signal for this bit cell, and we use word line for activating or deactivating this bit cell. And then what is the pin 9? So if you see this memory component, you can find that the data. You can find a data port. So actually, we can access data inside of memory through this data port. So which means a wire, electric wire, needs to be connected to this data port. So this pin 9 is used for reading or writing data to this cell. Okay, so we can read a data stored in this cell using the pin 9. Also, we can write a data to this store a bit cell using a bit line. Okay, so we use bit line for read or write of data. Okay, and then we use word line to activate or deactivate this cell. So, for example, for the read process, we first activate this word line. So if the word line becomes 1, okay, 1, then this line is activated. Okay, so this line is activated, and then the bit data is connected to this bit line. Okay, then we can read the data stored in this bit cell through the bit line. Okay. Also, what is the write process? The word line is activated, then this cell is connected to the bit line. Then we can write this bit line with some voltage, and the data is stored in this cell. This is the write process. So you can understand the basic structure or basic behavior of memory component like this. This is the cell, and then we just store the 1 bit data, each bit data inside of the cell. Then we use word line to control the activation or deactivation of this cell, and then through the bit line we can read or write data of this bit cell. So this is the basic memory structure. And then all type of memory, like the RAM, SRAM, flash memory, then any other type of memory includes actually use this structure. So all type of memory works like this. Okay, all type of memory works like this. Okay, so we have word line, and then word line activate each word, and then through the bit line we can read or write the data inside of the memory. Okay, let's see how the memory is composed. So if the memory includes the many bit cells, then we can store many data, right? So this is the detailed structure of memory component. So what can you see? So you can find the data port here. So this is the data port, and then the width of the data port is the 3 bit. Then what is the depth? So I said, so this is the data port, and then also you can find that bit 9. Each bit 9 is connected to the data port with is memory component, right? Then what is the word? What is the word of this memory? So you know, this is the data width, this is the data width, so this is the data word. Okay, so we can store 3-bit data for each word inside of this memory. So how many words exist in this memory? 4, right? So which means the depth is for this memory is 4. Okay, there are 4 data elements. So because this is a single word, and single word. Okay. And then as you can see, you can find that word line. Each word line is connected to each data element, right? So it's a word line, and then you know this is the single bit cell. So as I mentioned, there's this word line is connected to the control port of the bit cell. And then the data is accessed by this bit line. Okay, then in order to access the data inside of this memory, then we need to activate one of the word line, right? So I mentioned that in order to access, so we have to read and write. The access means that read and write. So in order to access the data, then we need to activate the one of these word lines. Okay. And then in order to activate the one of the word line, then we need to give address. Right? But so there are 4 words in this memory, and then the big width of address is 2 bit, right? Obviously. And then with the 2 bit address, then we need to activate the 4 different word lines. So which means that we need to activate the one over word line. So for example, if the address value is 01, okay, then we need to activate this word line. Okay, so which means it's data 1. So this is the decoder. So decoder receives the address value, and then decoder generates the individual word lines. This is the example of 2-4 decoder. So using this 2 bit of address, then we can control the 4 different word lines. So we can the address is given to the 2-4 decoder, and then decoder generates the one signal for this word line. Okay. So if the word address is 01, then this word line is activated, then we can access this word. Okay. So for the read process, then stored data can be read through these bin lines. And then write process, if these cells are activated, then we can write a certain data to this cell. Okay, so understand? So that's the basic structure of memory. Then as I mentioned, every memory includes this array type structure. Okay. Okay, so let's see those different types of memory. The first type is the random access memory. So I believe we can know the property of the random access memory. So we can write new data to random access memory. So which means that this is the writable memory. And then another property is the volatile. So volatile means that this memory will lose its data when power off. So like the DRAM. So we can, the example is the DRAM of our computer system. So if we turn off our computer, then the data inside of DRAM will be erased. That's why we require storage devices, right? So because the data inside of the DRAM is erased. And then another property is that we can read data for this DRAM, right? Obviously, and then we can write quickly. What does that mean? DRAM is fast. The RAM is fast. So we can write data to this RAM, random access memory. So which means that we can write a certain data very quickly. So which means that the speed is very fast for this RAM. That's why we can say that for DRAM is faster than our storage devices. So example is the main memory of our computer system is RAM. Okay. So actually the name of this random access memory is really weird, because actually the definition of this random access memory is the writable. So it's like the read and writable memory. So actually the text type is the read only memory. So which means that actually the random access memory represents the writable. the read and writable memory. Okay, but it's a historically, so this is the historical reason why the random access memory is called a random access memory. Okay, so it can be random. So random. So we can access the certain data inside the memory. So randomly. So or we can read and write a certain data randomly to this random access memory. So that's why this memory is called the RAM. So random access memory. But you can understand. So you can you need to memorize the property, the main properties of this RAM. So the first property is the volatile. So if the power is turned off, then the data is erased. Also, we can write data very quickly. That is the main properties of random access memory. And then another type of memory is ROM. It's a read-only memory. So the properties of ROM is the first property is non-volatile memory. The non-volatile means that the data is kept inside the memory, even though the power is off. So, flash memory. The first memory is the example of ROM actually. And then the name of this memory is read-only memory. So we can think, oh, you can write my data inside of the flash memory, right? So if not, then we cannot store our data in the storage devices or SSD, right? But I said flash memory is read-only memory, right? Why? Another property of ROM is that we can read data quickly, and then we can writing is impossible or very slow. That is the property of ROM. So for example, this is EEPROM. So EEPROM represents the electrically erasable and programmable ROM. I think that is the definition of the EEPROM. So actually, this is writable, but write process requires very high energy. So this means the write process is very, very slow compared to the read. So that is the property of read-only memory. And also the flash memory. The flash memory is the kind of read-only memory. So you may think, oh, flash memory is the best because the flash memory is flash because it needs fast, right? But compared to DRAM, flash memory is slow, much slower than DRAM. It is because the write process is very, very slow. Okay. So this is the ROM. So this is the first property of ROM is non-volatile. The data is stored even though power is off. And then we can read quickly data from the ROM, and then we can write. Writing is impossible or very, very slow. That is the property of ROM. Okay. Let's think about the RAM. So there are different types of RAM. Okay. So, but usually we can say there mainly there are two representative types of RAM. It's dynamic RAM. It's called the DRAM or SRAM. So D represents the dynamic, and then S represents static. Okay, so there are two types of RAM. Okay, and then how can we distinguish these two different types of RAM? So So these two different types of RAM is differentiated by how memory stores data. It means the structure of this cell. I mentioned that this structure. So this is the word line, and then this is the bin. This is the word line, and then this is bin line, and then this is the cell of memory. This structure is common. This structure is common for every memory type. Okay, this is common. Then what is different? This part is different. This part, which means how to implement this cell inside the memory. So it differentiates the different types of memory. So it decides the different types of memory. That means how we implement this cell. So this is the common structure, but this cell type. The implementation of this cell decides the different types of memory. Then DRAM. DRAM uses a capacitor for implementing this cell. And then SRAM uses cross-coupled inverters. Okay, so let's see the detailed implementation of this DRAM. So I mentioned that the DRAM use a capacitor for implementing this cell. So this is the structure of the memory. And then for this part, for the B cell, the B cell part of DRAM looks like this. So if you see this figure, you can find that the word line is connected to the, what is this? This is the gate of the NMOS transistor. And then another node of this NMOS transistor is connected to the, what is this sign? What is this symbol? This is the capacitor. Okay, and then another node of this NMOS transistor is connected to the bit line. So this is the basic structure of one bit cell of DRAM. And then data. The data is stored inside of this capacitor. So what does that mean? So actually, in the very first chapter of this course, we learned that the Z1 represents the high voltage, and then 0 represents the low voltage. And then what is the high voltage in the capacitor? If there are many positive charges in this capacitor, so which means that the voltage level of this capacitor is high, which means 1. So 1 is stored in this capacitor. Otherwise, the less small amount of positive charge is stored inside of this capacitor, or then it means the low voltage, which means 0 is stored. So you can understand that, so this is the structure of the common memory, and then for this DRAM, so DRAM, the data is stored inside the capacitor, the electric charge, and then this connection to the pin 9 is controlled by this NMOS transistor, and then the gate of NMOS transistor is connected to the word line. So this word line can activate or deactivate the connection to this pin 9, connection between the capacitor and pin 9. Understand? So this is the basic structure of the DRAM. Okay, so our industry, is very high, strong. That actually, DRAM is a very important industry in South Korea. So, let's see how this DRAM works. Okay, if the word line is 1, then what will happen? So word line becomes 1, then this word line is connected to the gate. The gate of this NMOS transistor. So if this signal is 1, what will happen? This NMOS transistor is turned on. It's turned on. What does it mean? This bit line is connected to the capacitor. So which means that we can read the data. So data stored in this capacitor. But actually, I said that electric charge is stored in this capacitor. So data read means that the stored electric charge is moved to the bit line. That is the data read. Okay. So in digitally, we can simply think that 1 is stored and it's connected, then we can read 1. Right. But actually, in a real world, electric charge is stored in the capacitor and it's connected. The electric charge is moved to the bit line. Then we can detect the change of voltage level in bit line. Then we can read the data. That's how it works. Then, if the word line is 0, then this is 0, then NMOS transistor is turned off, and this is disconnected from the DRAM. So, because the capacitor is disconnected from bit line, so this is disconnected, then we can store data. So, which means this electric charge cannot move to anywhere. So the electric charge can be stored inside of this cell. So this is the stored state. Okay, this is the behavior of DRAM, the basic behavior of DRAM. And then if we understand the behavior of NMOS transistor connected to this capacitor, then I believe you can easily understand the behavior of DRAM. So, but we need to understand actually the behavior, the real physical properties of DRAM is it's not simple. It is because electric charge is stored inside of the capacitor, which means that actually this capacitor is not a perfect capacitor. So what does that mean? What is the perfect capacitor? Perfect capacitor means that if this capacitor is disconnected from any node, then the electric charge is stored inside of this capacitor, and then the amount of electric charge is not changing. That is the perfect capacitor. But there is no perfect things in our real world. So actually, the electric charge is dissipated. So dissipated means that even though this capacitor is disconnected, a small amount of electric charge is dissipated. So which means that it's removed from this capacitor. Okay. So what will happen if the electric charge is dissipated? So I mentioned that in order to store our data, then we need to store electric charge. But if the electric charge is removed, then our data will be erased. Okay, our data will be lost inside of the DRAM. That's why. So in order to avoid this case, then we sometimes refresh the data stored in DRAM. So actually, the behavior of DRAM is a little bit complex, but it's not simple. Okay. Okay. So this is the real figure of it, how the DRAM is really implemented using the semiconductor technology. So actually you can understand that this is the word line, this is the line. Actually, this is the capacitor. Okay. So actually the DRAM process is a little bit different from our normal semiconductor process. So because we need to generate this very deep capacitor inside of the substrate. Okay. But actually, normal semiconductor process, there is no this capacitor, but not to implement the DRAM, then we need to implement this deep capacitor. That's why. So the DRAM is in the outside of CPU. It is because DRAM manufacturing process is different from the normal semiconductor process. Okay? So sometimes we can say that semiconductor process, semiconductor industry can be classified as the memory industry and non-memory industry, right? This is because the semiconductor process is different by the memory process and then non-memory process. So as like DRAM. So in order to manufacture DRAM, then we need to implement the capacitor, and then the capacitor is implemented like this figure. This is the real photo of the DRAM. Okay, so you can find the capacitor. Okay, and actually the electric charge is stored in this capacitor. Okay. Okay. So DRAM is mainly used as the external memory of the computer system. And as I mentioned, but it is because the DRAM manufacturing process is different from the normal CPU or SoC manufacturing process. Okay. What I explained, and then let's learn about the SRAM. So I also mentioned that this is the common structure of the memory, and then only this part is different. Then we can implement the SRAM using the closely coupled inverter. What does that mean? But I believe some students can recognize this is the very familiar circuit we learned in the previous lecture. What is this circuit? No, you don't know. Right. This circuit is the bistable circuit, actually. So this is the closely coupled inverter. And then when we learned about the bistable circuit, and we also learned that data stored inside of the bistable circuit, right? If this is 1, okay, if this is 1, then this becomes 0. And then the closely coupled inverters write the each value. Okay? So, and then we can store this data and then this data inside of this bistable circuit. It means closely coupled inverter. So with the closely coupled inverter, we can store data, the bit data, and we can use this circuit as the bit cell of memory. Then this is the SRAM. So S means the steady. And then actually DRAM means the dynamic. Then why did this steady memory? Because actually SRAM is stable. So what does it mean? In the SRAM cell, so I mentioned in the DRAM, the electric charge is stored in the capacitor. So which means that this electric charge can be dissipated. So which means the amount of charge can be changed by time. That's why the DRAM is called dynamic. So dynamic means something can be changed by time. But SRAM means the S represents steady, is because, so in this circuit, this is the inverter. So this inverter is driving this data continuously, driving. So which means actually the voltage level of this data is stable. Okay, it's not changed by time. That's why this SRAM is called the static memory. Okay, so unlike DRAM, the SRAM is very stable, but we don't need to refresh data inside of the SRAM. And then it's actually this part is only different. This is the only different part of the SRAM. As you can see, this the two nodes of this bistable circuit is connected via NMOS transistor, and then gates of this NMOS transistor is connected to the word line. So which means it's the same. Using this word line signal, then we can activate if the word line is 1, then we can read the data from this well, it's a bistable circuit. Then or we can write the data to this cell. Okay, this is the SRAM. So I said only this is the different part. Then why do we use the RAM instead of SRAM? So you know, I said that SRAM is more stable. So more stable than the RAM. And then also we don't need to refresh data inside of the SRAM because the data, the electric charge level is maintained inside of SRAM. Then why? Why do we use the RAM as main memory of computer system? Because of cost. What does it mean? Right? Why? So I show the real picture of real photo of the RAM. So actually, if you see this cell of the RAM requires one NMOS transistor and very deep capacitor. So which means, so in order to implement one bit cell, actually DRAM one bit cell requires one NMOS transistor only. Okay, so capacitor, we can implement the capacitor vertically because which means we can reduce the area of this one bit cell. But how about SRAM? So SRAM stores electric charge, so SRAM stores data inside of the cross-coupled inverters. So which means SRAM does not require capacitor. Which means SRAM can be implemented inside of the CPU because SRAM, in order to implement SRAM, you can use the same semiconductor technology. Okay, because there is no capacitor. But in order to implement the inverter and most transistors, and actually inverter requires the two transistors, like one NMOS transistor and one PMOS transistor. There are two inverters. So basically, in order to implement the one bit cell of SRAM, then this bit cell requires 6 transistors. And then DRAM requires only 1 transistor. So actually, the area for this one bit cell of SRAM is larger than the area of DRAM cell. And then why area is important? We want to store more data inside of the same area. So which means if the area is the same, then but we want to store more data. And in order to store more data, a single cell needs to occupy the smaller area, right? Obviously, right? So the area is the same, but in order to store many data, then a single data need to occupy a smaller area. Okay. So with the DRAM, we can reduce the cost because the DRAM itself includes only one transistor. Also, the size of single DRAM cell is smaller than the size of SRAM. So we can store more data using DRAM. That's why we use DRAM for store DRAM as main memory of computer system. So if we just we can just compare the properties of DRAM and SRAM like this. Actually, DRAM, the cost is low, then its density is high because the size is small, and then it's slow. It's slower than SRAM. Is it because actually the DRAM is unstable compared to the SRAM, so DRAM is slow. But SRAM, the cost is high, density is low compared to the DRAM, then it's fast. Okay. So actually, in the computer architecture course, we learn about the memory hierarchy, and then memory hierarchy utilize these different properties of SRAM and DRAM. Okay, that's why I explained the different properties or different characteristics of DRAM and SRAM. So you need to understand. For DRAM, cost is low, density is high. We can store many data, a lot more data, and then low. SRAM, cost is high, density is low, and then fast. Okay, okay. So this is the comparison between SRAM and DRAM. Okay. Sometimes we can implement the multi-port memory. The multi-port memory means that there are multiple address ports and then there are multiple data output. Okay. So as the port is actually the memory component is composed of address port and data port. Okay. And then actually when we mention a port for memory, port represents the address and data port pair. Okay. So one port memory represents this memory has one address port and one data port. So this is the single ported memory. But we can implement the multi-ported memory. This is the example of three-ported memory. So then this memory includes the two read ports, which means that one address port and one read port pair, and then another address port, and then another read port pair, and then one write port. One address port for the write port, and then write data port. Okay, so this is the example, three-ported memory. So sometimes we can implement memory like this. Actually, this is the example of register file. We will learn in the computer architecture course. Okay, the multi-ported memory. So we can just implement the multi-ported memory. Okay. Okay. And then ROM. So ROM is very simple. Okay, actually ROM is the read-only memory. Actually, so we can just connect some this word line and bit line. Okay. So so this is the example. So so ROM is so actually this example shows the read only. So which means that we cannot write any data. So writing is impossible for this ROM. So it means the inside of the ROM we just store a certain data, and then this data can be only read from a certain word activated by address. So this is the ROM. And then we can use that representation. So which means the word line is connected to the certain bin line, may represent the 1. Okay. So this is because if this is 1, then this 1 is just connected, and then data is 1. Okay. So we can, and then actually this is the actual data stored in ROM. Okay. So 0, 1, 0, and then so this word line is just connected. Okay. Then we can read 1 for this data port. This is wrong. Okay. Actually, it's very simple. Actually, with the ROM, then we can implement something called logic gate. So this is the example. So actually, in this example, if the A, so if we just focus on the data 0, right? The address, and then the address has the 2 bit, and then data 0 is only 1, only for A1 equal 1, and then sorry. No, right. A1 is 0 and B1 is 0. Right? Okay. So actually, we can implement the basic logic gate using the ROM. Okay. So if we just focus on the data 0, then A1 is 0 and B1 0, and this is 1. Otherwise, it is all zeros. So this is the example. So X equal AB and A plus B and G equal A exclusive or B. Then how can we implement the ROM for this logic gate? So we can implement the AB like this. Okay, so this is A comma B. So you have to implement the AB, so which means the A equal 1 and B equal 1, then it is 1 only. So actually, if we just connect this line, then this is the X means the A, B, right? And then you can also A plus B like here. Okay. And then A exclusive B, then if we just store data like inside of the ROM, then we can implement the X equal AB, Y equal A plus B, and then C equal A exclusive or B. Okay. Okay. So using the ROM, then we can implement the lookup table. So what it means, so if the ROM is programmable, then we can implement any basic gate using this ROM, right? So this is the example. So this, if we just change the stored bit inside of the memory, then we can implement the basic logic gate. And then this component is called the lookup table. So which means using the programmable memory, we can implement any basic gate. Right. Okay, so memory modules can be actually implemented like this. So actually, so until now, so we just I just shows the very simple memory component. So this memory just stores the small amount of data, but actually the memory is very large. So recently the smartphone also includes the 4 GB or 8 GB of main memory, right? So actually, this is the real implementation of our DRAM. So there, okay, in order to store many big data, the DRAM cell, there are many DRAM cells, and then not just the many DRAM cells, we have very large low decoder and then column decoder. Okay. So this is the example implementation of the SRAM using system variable. Okay. So actually we use SRAM for the internal memory or register file. So we will learn about the internal memory and the cache memory, and then we also learn about the register file, the computer architecture course, and then we can implement these memories using SRAMs. Okay, so you can implement the SRAM like this. Okay, so as I mentioned, we can implement memory, or we can understand the behavior of memory as the data array. Okay, so you can find this is the width of data, dB. Okay, dB is 32. That is the width of the data. It's a 32-bit data, and then you can find the multiple elements in this array. So we can declare array data like this in system variable. Okay, that is the width of a single element, then the depth of an element. Okay, so in this example, the depth is the 1024. So this data array includes the 0 to 1023. Okay, so array we can just set array number like the 1002, 0 to 1023. And then how can you read? For read, if the address is given, then we can just read the data array. It's simple, right? It's a read. And then how about the write? So actually this SRAM works with the clock. And then this SRAM is called the synchronous SRAM actually. Because the SRAM works with the clock signal. So at the positive of clock, then this SRAM receives the write init signal, and then by the address, this is the target words of SRAM for data in is stored. Okay, this is the write process. And then, this is the behavioral model, not actual DRAM. So even though we write the code, system variable code like this, actually this code will not be synthesized. Okay, but so we need to implement the real SRAM using the memory compiler. So this is also another chapter 2, and then we just replace this block in our real design. But for simulation, we require behavioral model in system variable. Then we can write the memory module like this. Okay. So ROM. So ROM is the simple word, is simpler than RAM. Okay, because this is the read only. But you can find this part. Actually, for this ROM, then the data is pre-installed. The data is pre-stored inside of the ROM. So actually, this is the read process because same to the SRAM. Okay, the out is indexed by address, and the data is read from the memory. Okay. But we need to initialize the array using a certain data, then we can use this process, this initial process. So the meaning of this process means that we can read data from the ROM.data file, and then we can just store this data inside of this data array. Okay, so this is the initial statement, so it will not be sensitized, not sensitized. Okay, this is the example of ROM in system variable. Okay, this is the end of the memory component. And then I will quickly explain about the PLAs or FPGA. So PLA means the programmable logic array. So which means that we can implement the logic using this PLA. And then FPGA means the field programmable gate arrays. This is also we can implement any digital system. What is the logic in FPGA? Okay. So actually, this is old. So we do not recently do not use the PLS frequently, but we frequently use FPGA because we can implement any digital logic in FPGA. Okay. So PLA just implement the two-level and or logic. Then actually we can change these connections. Okay. And then FPGA is composed of a logic element, and actually this logic element is the lookup table. Then I mentioned that with the lookup table, we can implement any logic gate, which means that we can change the output of this gate. We can implement the AND gate, OR gate, but exclusive OR gate using the lookup table. So FPGA means that FPGA includes many lookup table. And then using this lookup table, we can implement any logic gates. Okay, that's why we can implement any digital logic inside of the FPGA. And this is the hardware, so we can run our implemented logic using FPGA chip. But this FPGA is much slower than the real chip because it uses the lookup table. Okay, but it's programmable. So it looks like this. And then actually, modern FPGA also includes some cores like the ARM cores like this. So this is the example of the modern FPGA. And then modern FPGA for SoC design. Okay, Xilinx G 7000. And then this 7000 Xilinx G includes the ARM core. Okay, so which means we can implement our SoC design using this FPGA. So we can also run any operating system using the ARM core of this FPGA. Okay, this is the development board by Xilinx. Okay. So this is the example. Using the lookup table, we can implement any logic gate. Okay. So using the FPGA, then we can actually using the FPGA. So like using this FPGA board, we can implement. So we can program our hello code inside of the FPGA, and then we can run our hello code physically in the real world. That's the benefit of the FPGA, but it's very, very slow. So the FPGA chip is much more expensive than the real ASIC chip. Okay. So this is FPGA, and then you can read the chapter 4.5 and then 4.6. Close this course. So this course we learned about these topics like basic logic gate, and then CMOS transistors, and then Boolean algebra, something like that. And then and then the layer of the computer system. Actually, in this course, we handled these layers, like the logic layers and then digital circuits. Then what's the next step? Operator. Okay. The next step is the operator of the computer system. Like if we learned about this logic chip can be implemented using basic logic gate. Is a logic gate. And then the next step is architecture layer. Okay. So microarchitecture layer and then architecture layer of the computer system. Then also the operating system, blah blah blah. We start from the lower layer to and then we go to the upper layer of the computer system. So for the next semester, I believe the computer architecture is the mandatory course in the computer engineering, right? So I believe that you need to take the computer architecture course. So actually these two people, the legendary people in the computer architecture field, they will learn using the this textbook written by these legendary people. Okay. Okay, so I think I will teach the computer architecture course in the next semester. Okay, so hopefully many students can take this course. Okay. Okay, so thank you for your effort for this course, and then good luck for your final exam. 감사합니다. 수고하셨습니다.